now we need to talk about one more idea before we get into the maximum and minimum problems. So this definition says, given the function z equals fxy, the point x naught, y naught, fx naught, y naught is a saddle point if both, this is supposed to be fx. So fx, x naught, y naught equals 0, and fy, x naught, y naught equals 0. But f does not have a local extremum at x naught, y naught. So this is what we see below here. This down here, if you look at the center here, definitely need to use a different color there. Red will show out. Let's say there. So what happens is I get this drop down here, but it looks like it might be a minimum, but then when I go this way, it now looks like it could be a maximum. And that's what they're getting at. Now keep in mind here, oops, this is still a critical point because my partials equals 0 at that point. So keep that in mind too. So that'll happen. So first, if my gradient is 0 there, then that's going to tell me it's a critical point. And now with further investigation, that critical point could be what we call a saddle point, which is neither a maximum or a minimum. And as you can see how that could look by looking at these paths in different ways, that it could look like a maximum and it could look like a minimum. And that's what happens when we're dealing with some of the math there. It seems a little conflicting, but when you see the picture, it clears it up. Okay, so we need to think about this idea of saddle point. So let's move on now. Let's take a look at this example here. The second derivative test is another one here that allows us to classify these critical points as minimums, maximums, or saddle points. The saddle points we just discussed a minute ago. Okay, so anyways, let's take a look at this second derivative test. So it says let z equal fxy be a function of two variables for which the first and second ordered partial derivatives are continuous on some disk containing the points x naught, y naught. Suppose partial with respect to x and the partial with respect to y equals 0. Define the quantity. Now this is the part where it says, hey, they're critical points. And then this is just the handy dandy formula here that we're going to use. So this is fxx, fyy, and then fxy squared. Now this formula comes from what we call the Hessian Matrix. So if you're interested in that, you can look that up to get a little deeper idea of what that is. I'm not going to get into it here because I want you guys to try to understand how this all works together. It's going to be enough to understand that. So now take a look at this. So if, well, first, it's a critical point. And then if d is greater than 0, then f has a local minimum at x naught, y naught. Oops, I missed something there. And fxx equals 0. Now, the way I look at this is when we take the second derivative in Calc 1, that usually tells us concave up or concave down. Now, if it was concave up, that means it was positive. Now, I'm talking about second derivatives here in Calc 1, so in an xy plane here. Okay, so if that second derivative was positive, I had concave up. And if that second derivative was negative, which means less than 0, it was concave down. And we all remember this time here. And if you look at what this says here, if d is greater than 0 and fxx is greater than 0, that second derivative, then f has a local minimum at x naught, y naught. So if my second derivative in Calc 1 was greater than 0, then notice it opens up, which tells me that would be a minimum. And that's the same thing we see here. So that intuition we had back then, if you still have it, applies. That's kind of what I like about this. That's actually one of the things I like about it. It keeps it kind of simple in a way. So now the other one, if my d is greater than 0 and my fxx is less than 0, now think about what that meant in Calc 1. That second derivative was less than 0. That means it was open down. Now look what happens here. Then f is a local maximum at x naught, y naught. So that's what we would see here. So again, those ideas actually carry over here. That's kind of what I like about the second derivative test here. The only added condition is this D function. So that's the only difference here. So again, you'll have your book to take the test with and quizzes. So you'll have that formula with you. It's just a lot of computing. I think that's the other thing about it. It kind of sucks. But it is what it is. So anyways, now if D is less than 0, then F has a saddle point at x naught, y naught. So if it's less than 0, then I know right away if that's negative, then I know that I'm done and it's a saddle point. Any negative number. It could be negative 1042 or some crazy outlandish number. Now number 4 here, condition 4 says if D equals 0, the test is inconclusive. So there are those conditions as well. And once it's inconclusive, then I have to take a more analytical approach. And that's what we had in Calc 1 that we called the first derivative test. So we'd have something along those lines to actually talk about the surface of the surface that we're dealing with at that particular point. And maybe take paths in, start to get more analytical about it. So the next video, I'm going to cover this problem in it. But again, I wanted to give you all the ideas with the second derivative test, with the saddle points, so you can fully understand those conditions together before we actually get into these problems, because when we get into them, it's going to be, okay, I get it. It's not that bad. Definitely going to be a lot of work because I'm finding double derivatives of things, and then I'm squaring and summing and doing all that stuff too. So there it is.